So we've all made it onto the final lecture of the Quantitative Data Analysis Statistics lectures. Well done to everyone, although we're not quite finished just yet. In this presentation, we're going to look at some of the things that you can do beyond the crosstabs, beyond the correlations, and beyond the comparing of different groups. Again, these are built on similar foundations of things about parametric and non-parametric, about normal distributions, about linear relationships. All these kind of factors go in, and the types of variables we're using will determine the types of measures, the types of stats tests that we can run. Some of the models that we could run, the kind of parametric versions of things, will be, you'll come across these terms, and this is just so you're aware of them. Regression, you can have linear regressions, logistic regression, multiple regression, and the different types just depend on the types of measures that you've got in your model. So it depends on the types of variables, types of outcomes you've got. If it's a linear regression, you've got a continuous outcome. If it's logistic, you've got a categorical outcome. And if it's multiple, you've got obviously multiple outcomes. The categorical independent variable with more than two independent groups is when you'd run a test called an ANOVA, or an analysis of variance. So two categorical independent measures for more than two independent groups. So that's where you potentially measure lots of different factors. So age and sex, and say socioeconomic status, previous health conditions, and you're looking at one outcome of interest, a continuous outcome that you're interested in. So you then want to consider all these factors in together. So that builds on the kind of simpler regression models to add in this fact that you've got multiple categorical independent variables. If you've got repeated measures within that, you do what's called a repeated measures, ANOVA. So a bit like we looked at before in the previous presentation with your t-tests and your Mann-Whitney versus your repeated sample t-test and your Wilcoxon. It's the same kind of idea, but here it's just adding in those slightly different characteristics of the variables that you're handling. Now, it's not always easy to remember these in the top of your head, and even as someone that does statistics and runs these models relatively frequently, I always have to remind myself of which model do I use and what's available to me. I've provided this web link, and it's available in Canvas too. It's produced by UCLA and their stats department, and it's basically a big kind of table on the first page that you get to, whereby you look at what type of independent measures have I got, what type of independent variables, what type of dependent variable do I have, and that allows you to basically does like a big crosstabs table to say, well, what type of tests can I run with that data? Is it ANOVA? Is it regression? Is it a correlation? Is it a Mann-Whitney? Whatever the test may be, this website will tell you which tests are available to you. And then it will also give you step-by-step instructions in SPSS, as well as some of the other software statistical packages that you could use, SAS and Stata and R. It gives you the code, it gives you a bit of text and interpretation of what the results mean. So it's one of the most useful tools you could ever find if you're doing quantitative methods, whether that's now as part of this module, or whether that's as part of your ClinDoc project, or whether that's research or work you're involved with in the future. I would recommend bookmarking this page and continually going to whenever you're doing any kind of data analysis. So let's look at just one of the examples to kind of give you a bit of a flavour of what we mean, and we're going to look at the simple linear regression. Now, the regression models and linear regression models are essentially the foundation of some of the much more complex types of statistical models that you might come across and you might yourself do one day. A simple linear regression allows us to look at the linear relationship between one normally distributed interval predictor and one normally distributed interval outcome variable. So it's similar to the correlations that we did earlier, but it gives us a bit more information about the relationship based on a simple equation. It allows you to make predictions about how your outcome will be affected by your predictor with a bit more confidence than the simple correlations that you're able to do. Now, a linear regression line has an equation of this form, y equals a plus bx. And so I'm going to explain what each of those terms mean on this slide, and then we're going to look at it visually in a graph where it's a bit easier to explain. So I'm aware this is probably towards the end of the day and you've been through a lot, but that's why we're going to take it step by step to explain this relatively simple equation And what it means is it's the foundation of regression and a simple linear regression, but it also forms the foundation of much more complex models. So that's why I think it's key that you get this as part of this teaching, so that it kind of informs your understanding if you then delve into more complex stats models and more complex topics with quantitative methods. So this equation we've got, this y equals a plus b x. So in this model, x is the explanatory variable, for example, age, or independent variable, and y is the dependent variable, for example, cholesterol. The slope of the line is this value for b, and a is what we call the intercept. So it's the value of y when x equals 0. Now, that'll probably be completely bamboozling to you, and I'm well aware of that. So let's look at it visually, where I think it's a lot easier to explain. Now, this figure on the left-hand side is where we've essentially done a correlation between age and cholesterol, but we're using the regression method of doing this. So we've got our equation here, which is also what you see presented up here if you were to do this in SPSS. This is essentially showing you the exact same thing as that y equals a plus bx. So here we've got cholesterol is the y, 86.28 is the a value, the b value is 2.82, and x is age. And you've also got this thing called the R-square. We won't worry about that too much. It's basically a measure of how the model kind of fits and how confident we can feel about this kind of linear relationship. Then you've got quite a lot of scatter here between the individual points compared to this best fit line, which is kind of related to why that R-square value is what it is. And we talked about that with the correlation ones before, about weak and strong correlation, so that's what the R-square kind of gives us an indication of. Now, let's look at this equation in a bit more detail. So y is, and we mentioned this before, it's the constant plus, so cholesterol equals the constant plus b brackets age. Now, if we look at our graph, this tells us that, and these are the numbers that have been created through a regression model, that cholesterol equals 86.28, which is our constant, plus 2.82 brackets, in this case, 56. And this gives us answers of 244.2. So how the hell did we get to this point? Okay, so let's look at the constant. So the constant is the point when your age value here, your x value, is at 0. And so if you were to look at where this line, we obviously don't have anyone who's age 0. 0 would be down here somewhere if we looked at this based on the scale. It'd probably be slightly even off the chart. And so what that equation is telling us is if this black line, this slightly bumpy black line, if we continue to draw that down to where we got to the 0 point, which would be down here, that would be this value here, 86.28. So if we had anyone in our samples, this is obviously theoretical, it couldn't possibly happen in terms of who we were able to sample, but if we had someone who was not even born yet, was on day 0, was just, let's say they're just born, they're on day 0, then their cholesterol, we predict with our model, is going to be 86 here. So it's down here somewhere, we can't actually see it. So that's kind of where the constant is. We've obviously got this idea of the linear relationship here, and we need to understand, well, what does this really kind of look like in terms of adding on to our cholesterol values? Now you can see as you go up the black line, as you go up as ages, if you went from 20 to 40, then you can look across every single line for every single age. So you could look up to 40, put across, we're going to be about 200. We could look at 60, we put our mouse up here, it comes across, it's probably 255. So that gives us an idea, if we were to look at one of these ages, where our cholesterol value might fall. And so the B value here essentially tells us what this slope is. So as we go up one value in age, how big does our cholesterol go? And what this is telling us is if we go from one value, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, we will add on 2.82 in terms of our cholesterol onto that kind of baseline level at age 0. So every time we go up a year, we have to add 2.82 onto 86.28. And so if we were, for example, interested in those who are age 56, and so we've got 56, let's say it's about here, then if we push our mouse up here, we can see that close to 250, just below 250 probably, which is what our number here, 244, is. So we've got our constant being down here at 86.28. We've got our slope, which is related to the 2.82. So every time we go up 1, we go up 2.82. And so we've done that essentially 56 times, and we've got up to our value up here of 244.2. And so a linear regression model essentially allowing us to do that. For any age, we can predict, based on our model, based on the data we've collected, what their cholesterol would be if we were to scale that up to the wider population. Now, in this sample, we can see here, we don't actually have anyone that was age 56. You know, we've got probably, this person is probably 58, this person's maybe 54, 55, this person's 53. So that's where we have to make some assumptions in our data. And that means that, again, we've only got a small number of people in our sample at various ages. We can then apply that to another population, i.e. the wider population, to then make some kind of guesses, some educated guesses about how people's cholesterol values will change as they get older. But obviously there's variation here, and so we're never going to be exact. But if, again, you're working in clinical care, you look at any of the prediction models you're going to use about people's expected outcomes, how they might survive in a hospital, or if we give them a drug, what might happen to them. That's all based on this whole idea of the simple linear regression, that as we say, we up their dose, or as the exposure to a virus goes up, a higher viral load, we then get different kind of outcomes based on that, and we can try and make predictions. It's what the Framingham risk score, for those that are aware of that, kind of uses. It's what, you know, so many of our models in healthcare use, has this foundation of we can make predictions if we know something about an individual's characteristic, you know, a risk exposure, in this case their age. We can then predict what the outcome that we're looking at might be, or where a normal range for that outcome may be. So, deep breath and time to take a bit of a rest before, hopefully you've managed to get through these materials before we catch up at 4 o'clock for the Q&A session. Before I leave you, I just wanted to go back to one of the slides I put up in one of the very early presentations, was about thinking ahead and the kind of next steps. And it's really feeding into if you're going to be doing quantitative methods as part of your ClinDoc project, or if you're thinking about doing it. And again, my advice is keep it simple. Some of the best RCTs are a two-group comparison requiring the t-test. You know, you don't need to do very complex statistics. These are kind of some of the foundational models that we use. And there may be other complex things that come into that, other things you measure, but you may not need to do that. Design your study knowing what stats test you will use. Don't make analysis an afterthought. So consider the types of variables you're going to measure, what your outcomes are going to be, and that will allow you to then look at what kind of analysis may I have to do. You won't necessarily know about the parametric, non-parametric element, but you'll know if you've got repeated measures in there. You'll know if it's not repeated measures. You'll know if you've got continuous outcomes or categorical outcomes, and that will all inform what the analysis is that you're going to do. And when you write your research proposals as part of your ClinDoc projects, then you're going to have to, again, show for NURT-D4 that you know what you're talking about, that you're planning ahead for some of the things you're going to do, even though you haven't done them yet. And that goes to understanding the test that you're going to use in your analysis. Having some of that knowledge around, you know, t-tests and linear regression, crosstabs and chi-squares, you know, that's all foundational knowledge that you'll be able to apply, particularly where you do a quantitative project, or even if you don't and you're reading about other people's work, when you're reading research papers or reports that come out, you can sort of say, I understand that test, I know what that test shows, and has the interpretation, has the justification been made in terms of how people present what they've found. So we will catch up on Thursday, the 22nd of October at 4 o'clock for an hour for a bit of a Q&A. If you've got any questions, I'm sure you will, about these lectures, about the exercises, and we'll look through that material as much as we can in the time that we've got. We also have a catch-up coming on the 18th of November if there's any questions that are left unanswered or things that you still have to work through and things come into your head. And then once you've attended the webinar on the 22nd, I would really appreciate your feedback on all of these lectures and all the exercises and everything we've done together, based on a little survey that I've got in Canvas that you can answer in the bottom of this presentation. So thanks for your time. Hopefully you've enjoyed these lectures, at least to some extent. I hopefully tried to sway some of you into using quantitative methods and realizing that it's not that scary, particularly if we plan ahead and we think about what we're going to do.